You have it here now?
Yeah. So you'll have 25 minutes to present and 5 minutes for discussion afterwards.
So I can start now, yeah.
Another 30 seconds or so.
Okay.
So I'd like to introduce Sveinn Ólafsson, University of Iceland, who'll be giving a plenary presentation. Go ahead.
Yeah, thank you, Peter, and thank the organizer to let me give a talk about this subject, which currently there are only 3 people active in this field, I think. But of course, it's part of LANR. But here we can see a recent view from Reykjavik, just to start with. This is, of course, old nuclear energy coming up in Iceland, volcanic eruption. But hopefully there are some other reactions going on there. So this is started in 2014 that I contacted Leif about his Rydberg matter research, and I've been cooperating with him and Sindre in Norway for many years, and we had some progress, and I will first go through what Leif Holmrid has said during his 30 years long research. He's 79 now, so he is not able to do experiments at the moment anymore, but he is still thinking about his results and publishing papers. And in Iceland, we have a lot of equipment available, since we are maybe 5 senior researchers in physics who have joined up in a very nice lab with different fields possible. And then on the small side here, we see I don't have the, do you see my, where I'm pointing? You see my pointer?
We can see your arrow, yeah.
Yeah. So these people here, they're just an in-house startup company who's doing thin film research, and we have recently got this new X-ray equipment and a clean room and a lot of stuff we can do here. But the Rydberg matter is, as Leif has studied for so many years, is just an excited state of hydrogen or potassium atom. And it doesn't matter if it's hydrogen or potassium. The only difference is that potassium has core electrons left, while the highly excited outer electron is brought onto a far out reaching orbit. And if you would go to a state where you have all these quantum numbers to a full extent, like here 544, you get a planar atom, and it looks like an orbit of some kind of ring. And these atoms can join up into a cluster and form something which was predicted by people, Russian guy, way back in 1989. And so for Leif is the only person who has been studying the clusters. You don't find any other work. So this is very strange, and why this is so sparsely populated with science is I'm not sure. Of course, Leif's work is a bit controversial, but when we come into this, I'm just novice in this field, and I'm still a novice in a lot of things what Leif has been doing. And but some things we have been able to do and see what he is observing. But the main experiment is his first claim that these open structures which you have of these clusters, they are very large, a lot of distance. But he claims that in this experiment that I describe here, that if he shoots laser close to this catalyst, which is this red here, it's iron potassium catalyst, where you're flowing the gas through and collecting things on this foil. And then here is the detector with a time of flight distance, 10 centimeters. And then he claims that the laser can disrupt these clusters, and you will have a flight time which is sometimes too short to beat it through. So what is going on, the photon from the laser is disrupting this cluster and taking away screening charge, which results that you have a Coulomb force pushing parts of the cluster far away from each other, and equating this potential energy to the kinetic energy of this. You see that the initial distance between these two parts in the clusters is proportional to the flight time squared. Simple stuff here. And then this paper here, where he actually is presenting his data, time of flight data. And he, on the right here, he sees the normal Rydberg master clusters. And while in the short time, we are seeing signal which he says is a break up of a cluster. And if you use the formula before, because the chemical distance for hydrogen is 72 picometers, so this is 1/30 or something like that. And nobody understands how this is possible with any quantum mechanical calculations whatsoever. But still, the data is there, and this experiment we have not been able to or we don't have the equipment to measure, but we can see this in our experiments. And he has then continued by making a large source and shooting the laser into a huge source of this. He has maybe 10 or 20 pellets of a catalyst down here. And if he goes to very high pressure of, say, 10 millibars, he gets this tremendous plume of plasma. But usually he's at lower pressures and measures the time of flight in different regions. And he has published a lot of papers here. And here is this picture of his lab, which is dismantled now because he is retired. And I have to just show you here. You see that there's a signal here almost at zero. So we are zooming in on this fast part here. Yeah, this is actually the slow part, but still gives this strange energy. And then you are able to see that the time of flight is very short. It can be few nanoseconds in his tube. And then he has postulated that this is decay of mesons and protons, and mesons mainly. And from the slope of this time, he has get something who looks like a lifetime of kaons and pions and so on. This is easy to see in our experiments, but and we have seen some of this decay time. But if all of this signal, if you integrate the current, and then you have a huge number of particles interpreted as mesons or muons, that you should be very easily to see if this is mesons or muons. And here you can see in Norway that we got this kind of a particle time of flight. And we can, in a sense, do a lot of experiment in this manner. So we see this fast signal, and the time of flight signal is still happily less than speed of light, because the first interpretation you can do on this is actually that what comes first is this huge light bar coming out of this here, and it should travel the speed of light here. But the signal he was coming here is still at half the speed of light. But of course, such huge light should affect anything on the way here. So what we have seen in Iceland later, this is the setup, old setup. Here we have the 5 nanosecond pulse laser shooting at target here. Here is the focusing arrangement, so we can focus this beam down to 20 microns or so. And then this time of flight here. And then we can actually see that when we are hitting with the laser on this tantalum foil, and here is the catalyst, and then we can get the same signal. And it is half the speed of light, so it shouldn't be a light. But light is not only a light, it can be a microwave pulse, because if you take a microwave source, let's say a microwave pulse coming here, then this line is nothing but a microwave waveguide, but a very lossy one, because this is stainless steel and usually copper. And the travel time of a microwave pulse is always less than speed of light, and it depends on actually on the wavelength of the microwave and the diameter of the tube. So we have been trying to rule out a microwave pulse and light pulse, and we are still not convinced. Hopefully with the newest experiment we can rule that out. But here is like something which is too fast, I think. I mean, this I did in Iceland, and this is almost speed of light. So then you start to wonder, are we really measuring particles here or not? But sometimes the situation in Iceland is that the base pressure is actually among the lowest, much lower than Leif has done. So this is the cleanest system so far. And this we will soon try to repeat and get rid of this nagging microwave idea. But this is what we saw when we took picture on this interaction with the laser. And if we start here, you see this is the focal point of the laser. And since this is light, but since we are shooting in infrared laser, so there is something going on here, and the base pressure here is actually 10 to minus 7, 8. So it's not a high laser pressure. Still, we see something here, like there's a gas who is excited. And while we move this focus picture closer to the tantalum, we start to see something who we don't understand, because we're still far away from this foil, and we are starting to see some kind of excitation and diffraction at the same time. I think you, Peter, you had some picture like this in your talk. Well, with excitation transfer, something like that. And going much closer, we see that it becomes more intense, and we are very close to the foil now, and there are additional lines coming up. And in the end, we start actually to hit the foil much better. And here in H, we hit it, so there's no visible light anymore. But actually, in figure 8, it is this is the occasion that you see fast particles. In in none of this A, B, C, D, and up to G, we see fast particles. So in a sense, we are ablating the tantalum foil, and something is coming with it. And as at the moment, we don't know if these are just fast protons or something else like muons. But of course, if you're shooting on hydrogen, you expect to see fast protons and fast electrons. If I going to more unrealistic muons or something like that. So now let's talk about the detection of this radiations, which is visible when you don't shoot with a laser. And you might wonder what is going on. It is just a PMT with a lot of signal from a aluminum foil in front of the PMT. And when you don't heat the catalyst and you don't have excited the chamber or anything, you see this difference, and this comes from the PMT. And Sindre is writing a paper about this history, starting with a no activated chamber and then this radiation coming up. Like here, you see without gas or without pumping, and then with electrolyzation and then just leaving it for a while and pumping, you see this signal coming up, and also in Iceland. And we're trying to see what kind of radiation this is. And here is like just last week data from Sindre. And here is just starting with a low activity chamber. Typical count rate for low activity is about 150 counts per second. So there's a little bit of activity here. And you see these wiggles. This is maybe sometimes appearing, and maybe it could be actually oscillation noise or something like that. But you see that we have the stable background counting rate, and the spectrum of pulses are looking very similar. But if it would be a completely dead system, this signal would be like this, going down here. And then Sindre comes in and pumps on the system, and this shows up. With different layers, you get this huge increase in counting from this photomultiplier tube. And the effect of number of aluminum layers is drastic. We have so far only used 4 layers, but we decided to check this again, and to our surprise, we see this huge increase when you have a lot of aluminum layers. So this is just under scrutiny, and we've seen new things a lot of the time. How many minutes do I have left?
You have 8 more minutes.
Okay. And seeing this in a PMT, you'd want to see something with your own eyes. And this is from Iceland when the chamber was active. And here you're seeing tracks which you normally don't see in cloud chambers. And there's a coming up at the end, very strange circular track with dots on it. Soon here at the end, yeah, this was it. So you can see it here again. So can anybody tell me what this is? And in Norway we have similar, but not as like this. This looks more like an alpha or something like that, but you never see double alpha taking a bend like this. So are we seeing dark matter in London? Is it a detector for dark matter? It's just a wild guess. So you can see here that things are pretty strange here when we are doing these experiments. So this is work in progress. So I think I will summarize something of these questions. You definitely see fast particles because, but we're not 100% sure. So we are doing better experiments with a better equipment and so. Also, what I didn't mention is that Sindri has seen occasionally a lot of neutrons, but not every time. So there is this possibility, before I describe this equipment, that here is the target. When you shoot with a laser, you could be accelerating protons from this condensed state of hydrogen. And if you have these very powerful protons on, say, 40 MeV or something, anything it hits, it spallates neutrons out of it. But the strange thing is that that happens not every time. So sometimes it looks like the target is giving neutrons and sometimes not. So it is, a puzzle. But here is the new setup, which will be hopefully up and running in 2 months, since I got an assistant who is taking care of building it and have some financing for me sitting a chair and thinking and designing experiment, and he's doing the work. You see that what is new here is actually we have defined a path with a collimator different, so we can actually collimate on different things, and we can here actually let it go through a detectors like these here. This is just a PIPS detector, so it can excite, if it's a fast proton, it can give a very nice signal in here. And also in this very thin silicon PIPS detector, it can pass through this, so we can measure the delta E detection here. And also we can add later here a magnetic filter here, so we can bend these things and see how these particles are their mass ratio depending on speed. And also then we have these 2 coils here, which you see here, it passes through this coil and we can detect them on different things. And here we can calibrate the current. Then on this here you have target 2, and this is a target where we are trying to make more higher amount of this hydrogen phase. There will be a lot of catalyst here, and we can shoot into it, and what is more, right on top of it we will have a valve, and here we can place different detectors who look directly through this hole onto this source here. This PMT detector, which is, if you can find it, it is on here. There's a double up here. Here's a neutron detector, and here is a neutron source we can calibrate. This source is not affecting the PMT in any way, but we know that X-rays affect this source greatly. So that is why we are planning this X-ray detector looking directly down into this guy here. And is there anything left here? Here you see the different holes from the collimator. We can choose what we collimate to. And then we have this constantly 24 hours radiation detector. And then this cloud chamber will be placed just right under target 2, so it will have a very good view on this target with a camera and so on. And I think, thank you for listening.
A nice presentation. Are there questions? I'm going to have to get some kind of view screen. Given that Graham has been raising his hand all conference long and never been called on, I'm going to call on Graham first. So Graham, add your question. Ask your question.
Me?
Yeah,
Can
Graham.
you- Okay, good. This is very intriguing work, Olaf. I don't know, your dark matter idea might not be too far off. There's what is the characteristics of your laser pulse? You said it's
Yeah, that is just a normal 5 nanoseconds mode locked laser. So
what's the energy on target, joules per square centimeter?
So it is 10 to 12 maybe.
Okay, that's pretty good. Because people are looking for axions, and I just thought an axion will be converted to a photon in a large magnetic field, and I thought that people who do laser work, high power pulses on a solid create really high magnetic fields and electric field. But also electric fields convert it. But there's so much mayhem. I didn't think there was any chance that you would be able to pick photons out of that. But in your system with that long arm that you have there, drift to time of flight tube, I'm intrigued by your half speed of light signal, which you say you think might be a microwave, which it could be. It could slow down that much and so so I'm just planting that seed that you might be converting axion dark matter to a microwave region photon, and if you could put a spectrometer on the end of that tube and look somewhere between 1 millielectron volt up to maybe 100 millielectron volts, which you can do with an IR spectrometer, you might find something really interesting.
What kind of spectrum detector? You mean?
Infrared spectrometer.
Okay.
A spectrometer that you can cover those ranges with a spectrometer. They're $50,000 to $100,000, but it could be very interesting.
Yeah,
and you can't have a window, but most of these microwaves actually get absorbed, and if you have a window, so you can put them in, have the vacuum go right into the spectrometer, so you don't have a window.
Yeah, but note that this signal is always there. You don't need the laser.
Oh, okay. I didn't understand that. Well, then just ignore what I said because to make it okay.
Okay.
Thank you.
Evgeny.
Thank you very much. Are you listening to me?
Yeah.
We can hear you. Go ahead and ask your question.
Thank you. Mr. Ólafsson, in your film, there was some tracks. Was there some kind of camera by Wilson? Or it was something another?
Yeah, what kind of chamber?
Huh?
I mean, this is just a cool surface, and you just place isopropanol on the top. So it's an isopropanol critical gas liquid. So you
gas and liquid.
Yeah, well, I mean superfluid isopropanol probably, which is creating the environment.
Is it tracks of strange particles in Russian literature and in Russian science? There is kinds of particles, strange. Is it equal to this object or no?
Oh well, you might maybe be able to send it to me. I have very little library of strange track. But of course, if I take this chamber and move it to my office, I don't see anything. Zero.
This tracks in the bust of thin films.
Yeah, it's just a surface layer of isopropanol, super cooled.
Thank you very much.
Okay,